This is part 7 in a series of videos in which I'm developing a logic comparator. It's a 40-channel comparator and will allow testing, in-circuit testing of devices with up to 40 pins. If you're not familiar with how these devices work, then they're quite straightforward. It's really just a series of XOR gates feeding into pulse stretchers. And the idea here is that one of the inputs to each logic gate is fed from your unit under test, which I'm simulating with this breadboard, and then you have a reference device on the test unit itself, and you feed the same signals into the device on the test unit that you are feeding into your unit under test. And you do that simply by clipping a test clip onto the device on the unit under test board. And the idea here is that any of the outputs on the reference device, which presumably is a working device, that vary from your unit under test device indicate that there is an error with the gate on the unit under test. Now, as with all digital electronics, it's never quite that straightforward. So the testing I'm doing at the moment is dynamic testing. I've been through and done a full static test with this to make sure that all the interconnections are correct and they're fine. But what I'm doing now is going through the dynamic design step of this device to see what its performance is and make sure that the values that I recommend for this are correct. So before I go any further with the demonstration of the testing, I'll just quickly explain how the circuit actually works. It's very simple, but if we have a quick look at it, then it will help to explain exactly what's going on here with the testing. Okay, so this is the basic circuit. Simplified quite a bit here just to make the explanation clearer, but there is one of these for each pin on the logic tester, and what we do is we feed one of the inputs to the XOR gate from our reference device, and the matching input from the device on the UUT goes to the other input of the XOR gate. The idea here is that what we're doing is we're trying to compare these two inputs to make sure they are the same. Now, if they're inputs to the devices, then they should always be the same because they're tied together on the module card. But if it's an output, then they are independent, and that's what we're trying to test. We're trying to see if the outputs from the device under test and the reference device are doing the same thing, and if they're not, then we know we have a fault. The output of the XOR gate is fed into a pulse stretcher, and it's an edge triggered pulse stretcher, so when we get an edge changing, then essentially what we end up with is a 70 millisecond pulse coming out of the pulse stretcher, and that's used to feed the LED. And the reason this is here, of course, is so that we can see the LED coming on. If we didn't have the pulse stretcher and we had very short glitches, then we wouldn't see the LED doing anything. Now, assuming we have two inputs going to the XOR gate and they are the same, then in theory we shouldn't see anything happening on the output, and so we shouldn't trigger the pulse stretcher and the LED should stay off. But as ever with digital electronics, it's never that straightforward. So we could end up with a situation, partly because of the physical layout of the setup. You know, we have the logic comparator is a separate device. It's on the end of a ribbon cable, and then there may be differences in the devices that we're using, which I'll demonstrate in a few minutes. So you could end up with a situation where the reference device is behaving like that. Bear in mind, you also have to take into account the rise and fall times, and it could be that the unit under test is doing this. And many things can cause this, but it is fairly typical in digital electronics. Now, this may only be a few nanoseconds, so let's say for example it's 5 nanoseconds, but that is enough to cause an edge on the output of the XOR gate that will trigger the pulse stretcher, and it will illuminate the LED. So even if these are essentially doing the same thing and they're both switching, it would trigger a fault display on the LED. So in order to prevent this, we need to essentially allow a settling window where we don't allow the pulse stretcher to be triggered, and that way we guarantee that we're allowing time for these to settle. And then the same going the other way, we want to make sure that we allow a dead band so that this allows them to settle when they're dropping, and vice versa. And to achieve that is very straightforward. We just put a capacitor on the output of the XOR gate. There are other ways of doing this, but this is the most straightforward way, and because we're talking of just a few nanoseconds, then of course it means that it's very easy just to put a loading on here, and that will be quite sufficient. What I'm doing at the moment is I've checked that all the interconnections are as they should be, so that's all working, and what I'm doing now is checking the if you like, the skew that's allowed within the system, and then tailoring the value of this capacitor accordingly. The bigger the value of this capacitor, then the bigger this deadband, and so the more scope there is for a skew within the two signals. But also, the bigger the value of this capacitor, the lower the maximum frequency is that the unit can handle. If these deadbands are always the same, then obviously what's going to change with frequency is the distance between them, and when this gets to 0, then the unit can no longer detect the edges within the switching. So what I'm trying to do is optimize the value to make sure that we're getting best case conditions between not being falsely triggered by skew and noise, but allowing the maximum frequency of operation of the unit. Okay, so bearing that in mind, we'll go back to the logic comparator, and I'll just demonstrate this in action so it fully clarifies what testing I'm doing and why. Okay, so the way I'm doing the initial dynamic testing is I have a simulated UUT. This is all powered up and connected. I have all the inputs from this particular device connected to the UUT this time. Again, it's a 7400. We'll be testing other IC types, but it's not just as simple as testing 7400. I need to test quite a few different types of 7400s from different manufacturers, and I'll come back to why that is in a few minutes. So at the moment I'm feeding it with a clock signal. The clock signal is coming from one of my signal generators, and it's going here through a 7404, and that is just to condition the clock signal so that it's essentially a TTL, a signal level, and the signal is not going to be modified or influenced by the output of the signal generator. It's currently running at 1 Hz. You can see this is this LED is flashing and is connected to the output of one of the gates on the 7400. Everything else, including this, is fed through to the logic comparator, and you can see at the moment there are no errors being indicated. Even if there was a very short duration glitch, then essentially the LED on the logic comparator would be triggered. It would stay on for about 70 milliseconds and we'd see it flash fairly clearly. If I disconnect one of the outputs that is going from the unit under test through to the logic comparator, just to demonstrate what would happen if this device wasn't working properly, we can see now that what's happening is the LED on the logic comparator is flashing, and it's doing that because it's detecting that the output of the 7.4 unit is not matching the reference unit or the reference chip. If I reconnect it, then you can see the flashing stops. This is running at 1 Hz, so what I'm doing here is I currently don't have these capacitors fitted. So this capacitor is not, there's nothing in that location on the board at the moment, so I'm just testing the stray capacitance on the board, the leads, etc., to see what its base performance is. I have tried fitting various values of capacitors, which I'll come back to in a minute. So we're running at 1 Hz. What we're doing here is looking to see how high a frequency the unit will operate over. So I'll start increasing the frequency. I'll go to 50 kilohertz. And we can see we're still not getting any error detection. I'll disconnect this input, and now the LED is on continuously, of course, because every time there's an edge we're getting a 70 millisecond pulse stretch, and that is re-triggerable, so essentially the pulse stretch is being continuously triggered by default. I'll reconnect this and the LED should go out. So as long as this is happening, then we know the unit's responding at that frequency. If it can't respond fast enough, then either we'll see error lights starting to come on when they shouldn't, or the error light won't come on when it should. So I'll start increasing the frequency. We'll go up to 500 kilohertz, and we can see there's no false lights and the error detection is still working. This is incidentally will work with any of the inputs or outputs. If I disconnect them, we'll see an error popping up on the logic comparator. It will go up to 1 megahertz, and we can see still no ghost errors, and it's still responding as it should to actual errors. We'll go up to 2 megahertz, so still looking good. Go up to 5 megahertz. And still it's behaving the way it should. I'll go up to 10 megahertz. Okay, and that's still looking fine. On the screen, if you can see it, it's saying it's 20 megahertz, but that's just because it's counting these noise glitches at the end. And the reason they're there is because we're feeding 2 inputs to the logic device on the UUT. And I'm doing that intentionally to make sure that there is noise present in the system. I don't want to be fooled into thinking it's working when as soon as we use a real unit under test, then it stops working. So this is kind of a worst case test, and bear in mind we have all these wires and things hanging around as well. So still working. Let's see if it's responding at this frequency, and it is. So we'll go to 15 megahertz. This is actually way beyond the frequency that I designed it for, and it will not operate at this frequency once we start fitting the damping caps. But this is just to get an idea of the raw performance, and it's still working fine. So we'll go to 20 megahertz. And you can see now we're starting to get ghost warnings, ghost errors. It's actually still kind of working, but you wouldn't want to run it this fast. It's starting to show false alarms. It might not actually do this on a real unit under test, but because this is kind of worst case testing, then that's what I have to aim for. So we'll go back down to 1 megahertz. And we can see it's now behaving itself. So it looks like it's working fine as it is, but at the moment the device I have as a reference and the device on the UUT are from the same manufacturer with the same date codes. So what I'm going to do is just swap over the device on the UUT for a different manufacturer type 7400. So I'll take that one out. As I say, it's still a 7400, but it's a different manufacturer type. Okay, power on, and then the clock back on. And as you can see, we're now getting false error lights that we weren't getting before. And this is caused, as I mentioned earlier, by the fact that this UUT device is a different manufacturer, and it has different switching characteristics to the one that we have on the logic comparator. If we were to put a matching device in the logic comparator, chances are these lights would go out, but obviously that's not really practical to use, and you don't want to have to find exact matches. And also, as I mentioned previously, as devices age, their performance changes, so it would be pretty much impossible to use like it is here. So that's specifically why these capacitors are needed, and it's really a case of finding an appropriate value. Now, the higher you go to a certain extent, the better. It gives you more scope for dealing with glitches and noise, but as I said, the higher the value of the capacitor, the lower the effective bandwidth of the tester. So I've tried everything from nothing to 10 nanofarads. 10 nanofarads works fine, except that it limits the maximum speed of operation to 800 kilohertz, and that's not really enough for digital stuff unless you're doing static testing. The ideal value seems to be about 470 picofarads, and that gives us extremely good immunity to noise and skew. Bear in mind, the skew is very small. We're talking about very small amounts here. It's just a few nanoseconds, but that's enough to trigger the pulse stretcher, which is what we're seeing on the LEDs. So that's the value I'll be recommending for these, is 470 picofarads. I'm going to fit a full set of 470 picofarads capacitors and then continue the testing throughout the speed range. With that value capacitor, it gives us a maximum usable speed of about 8 or 9 megahertz, which is more than enough for 99% of the units that I work on. If you need to use this on higher frequency stuff, then you can do that, just go down to maybe 200 picofarads, but if you go too low, you'll start getting this effect when you're picking up errors that don't really exist. Okay, so that's the board fully populated. I fitted 470 picofarad capacitors in the damping positions, and that should help remove the glitches that were causing the false alarms. So I'll get this plugged back together and we'll see if we've got the right values. Okay, so I'll power it up, clock back on, and as we can see, the erroneous error lights have now disappeared. Same situation we had before, we've still got the same different manufacturers of device, but now because we've got some damping of the glitches that could potentially come out of the first XOR gate, and we're kind of damping those out, then it's not triggering false warning light. It should still be able to detect the error, so if I disconnect the output, we see the error light come on as it should do, and it goes out. So we know it's now working at this speed, so I'll increase the clock frequency. In theory, with this value of capacitor, we should still be able to work pretty much up to somewhere between 15 and 20 megahertz, but we'll have to test that. It really depends on how good a job I've done with the board layout, whether or not it can handle frequencies that high. So we'll get up to 5 megahertz. It's currently on 1. That's 5 megahertz, and so we're not getting any false alarms. Let's see if it can still detect actual alarms, which it can. Up to 10 megahertz. So this is really the minimum I was aiming for. So we're not getting false alarms, and we are still able to detect alarms or actual faults. Up to 15 megahertz. It's still showing double frequency here than the actual clock, simply because we're getting this glitching because we have two different type gates connected together, two different inputs connected together. But that's the sort of thing we need to be able to deal with in real world test units, so we do need to make sure it can withstand that. Okay, so we're at 15 megahertz, no false alarms, and it can still detect the actual alarms. And then finally 20 megahertz, and sure enough it's still working. So very good result. We're getting good immunity to noise. We can see this is a very noisy signal we're feeding into it now, and yet it's not giving false alarms, but it is still picking up the errors when it's supposed to. It's working from DC right up to 20 megahertz. So what I'll do now is just slowly move the IC down one row at a time, making sure that I'm testing every single channel as both an input and an output across the entire frequency range. But it's looking good so far, and as long as it works on all these different inputs and as it is now, then that will be the unit finished and the design complete, and I'll then make them available if anyone wants one. Any questions or comments welcome, and as I say, if you are interested in one of these, then please let me know.